Earlier in this course, we talked about for loops and went over sequences that loops can work on. But this begs a question, what does it mean to be a sequence that a loop can work on? Well, to answer this, we have to understand what Python is doing under the hood in a for loop. Whenever we put an object in a for loop, in this case a list like this, Python is doing two things. First, it is attempting to convert the object into an iterator object using the iter function. If that fails, a type error will be thrown. For example, these are all object types that iter will work on: a list, a tuple, a set, a frozen set, a dictionary, and a range. The common theme here is that these all have a sequence type nature where you can iterate through them element by element. For this reason, iter can also work on, say, a string. So I can do print iter and then my name, a string. And the reason why we'll work on this is because a string can also be broken into a sequence of its characters. Examples where the iter function won't work will be an integer. So iter 1, it will throw a type error. Let's try a float, also a type error. And last but not least, let's try a complex. This will throw an error as well, because obviously these don't have a sequence type nature. So that's the first part. The second part is that once your object is an iterator, the next function should be able to work on it. And this is precisely what the for loop will do. It will apply next at each step of the iteration to jump to the next value in the sequence. This can readily be demonstrated by a list. So first, let's apply the iter function on it, iter, because we have to do the first step. Integers 1 to 5, great, okay? Now, let's apply next and see what happens. Print next L. So now it has jumped to the first element. What will happen if we apply this again? As we guessed, it jumps to 2, the second element, and if we do this 3 more times, it will jump to the remaining 3 in order, 3, 4, 5. But what if we try to apply next one more time? Well, now it'll throw a stop iteration exception because our list only goes up to the value of 5. After that, there are no more values, so there's nothing that next can retrieve. That's why it's throwing a stop iteration. So this whole process where it first applies the iter function and then it repeatedly applies the next function until a stop iteration is caught is what the for loop is doing behind the scenes. The reason why you don't see the stop iteration is because the for loop knows to stop when it catches that, okay? And with this very criteria, you can actually define your own iterator. So let's start with a minimal example. A simple counter where you start with 0 and you count up. So first, I'll create it, then I'll explain it. So class counter def iter return self def next self So this is the most minimal an iterator can get. You have to have these two dunder methods. You have to have the iter dunder method and you have to have the next dunder method. The iter dunder method emulates what would happen when the iter function applies to it, and the next dunder method emulates what would happen when the next function applies to it. The iter dunder method must do two things, because remember, when we're applying the iter function, the outcome is we want it to be an iterator. Well, if we're defining our class to already be an iterator, then you should return self because you're assuming there's already an iterator, okay? It's kind of like a chicken and the egg situation, where what comes first, chicken, egg, or egg or chicken? Well, it's already iterator, so you already return self. I hope that kind of makes sense. And then you have to initialize your beginning value. In this case, our counter will start at 0, okay? And the next method should return some internal value updated so it knows how to jump whenever the next function is applied. In this case, our value that started at 0 is being incremented by 1 each step. So now with this, if we put this counter into the for loop, let's see what we get. For item in counter print item. Let's run it. So now it is counting, but the problem is it's counting indefinitely. And the reason is because we forgot to throw the stop iteration at some point. So let me stop this. Let's say I want this counter to go up to the value of 9 and stop. So I can say if self.val equals 10, then raise stop iteration. So let's rerun it, and now it goes up to 9 and stops. We can even make our stop value user definable by creating an init and then specifying it there. So def init self stop val. I will default it to 10, and I'll say self dot stop val equals stop val. And now, of course, I have to reference that here. So self dot stop val. So now if I rerun it, it still goes up to 9 and stops because our default was 10. But now I can input a different value. Let's say I want to go up to 100. So now it will stop at 99. As we see down here, okay? And now this is actually looking a lot like a range object, but just for the case of one input. So just to see that, I'm going to compare it with the range. And that also goes up to 99. So we effectively created a counter that is like the range. Now one nuance I want to mention is where in your iterator you initialize your start value, because oftentimes this gets mixed up. Should you initialize it in the iter method or should you initialize it in the init method? Okay, so for a moment, let me initialize it in the init method, comment this out, say self.val equals 0. The problem with this approach is if the user were to create the counter outside of putting it directly in the for loop, say like this, c equals counter 100, and now I have to make this c. You know, I'll actually make this 20 so we don't have too many numbers. So if I run this, see, it seems to work fine, right? But the issue is, unless if this is what you deliberately want, a user could simply do this, c.val equals 10, and now it'll start at 10. Okay, so now every time our iterator goes into our loop, the user can change how it wants to start beforehand. But if you want to force the idea that you want to start at some predefined value every time, for example 0, then you should always initialize it in the iter method. I hope that makes sense. So if I were to take this out and put it back here, now if I try changing it, it's not going to have any effect. And the beauty of all this is, with what we now know, is virtually any object can become an iterator. For example, let's revisit our manager class. So let's say, let me bring back the employee class, but much more simplified. Okay, where I took out the salary property for a moment, and the str_dunder method, I took out the emojis, and I also took out the title. So I'm keeping it simple for now. Let's run it. And now if I recreate the manager child class like this, okay, again, I took out all the other methods, but obviously I have to put the employees into a list. So I have self.employees into an empty list, and then for employee in employees, first I have to check if each employee is an employee object. If that is true, and then I will append it to self.employees. Okay. So this is our employee revisited, much more simple, and our manager child class revisited, also simplified. And the idea I'm going for is this: since manager contains employees, I want to add the capability of being able to iterate through those employees of manager. So this is how I can achieve that. I can say def iter self, and in our case, the values that we are incrementing are just going to be the indices of employees. So indices starts at 0, so we're gonna set it to a -1. And you'll see why I'm doing this in a moment. -1, and then, like I said, you have to return self. And now we have the next dunder method, self.val, and then we increment it by 1. So the reason why it's -1 is because the very first time we applied the next function, we wanted to return 0, because -1 plus 1 is 0, because 0 is the first index. So that's why I have -1, okay? And now what I can do is this. I can say try return str self.employees self.val. Then I can say except raise stop iteration. And the reason why I wrote it like this is because you can have any number of employees. And the idea is you want to be able to cover all those employees. But once we were to get past all of our employees, this statement would essentially throw an index error, because with the list, if you go beyond the list, you get an index error. Then the except will catch that and then instead raise a stop iteration, because we're trying to emulate an iterator. So now let me run this. Now let's say I were to create a bunch of instances. I have Mohammed, he's an employee, his name, 6 years of experience, he's excellent, 5. You have Jill, Ali, Dave, Tina, Abdullah, and myself, Ahmed. Give myself an average rating, trying to be humble. And I'm pretty new, so 0 years of experience. So now, let me run this. Now let me define a manager called Bob, who takes in all these employees, Mohammed, Gil, Ali, all the way to myself. So now if I do for employee in Bob, do you think this will work? Print employee. Wait, why is it getting an error? Did I not run this? Let me try rerunning it. This should work. Oh, I see the issue because I indented this a little bit too much. So what I should be doing is, this should be, I think, tab. Okay, now that should fix it. So now let me rerun it. Let me run this, and then let me run this. So now it works. Now that we iterate through each employee of Bob, we're getting all their information because that's what we wanted. We have this str function to essentially call this str dunder method, and that's how we're able to get all their information. Now, one misconception that a lot of Python programmers make is thinking that iterators can be indexed or keyed. This is actually not true. For example, if we go back to our class counter, okay, let me create a counter, my counter equals counter 100. So that worked, okay? But now, let's try to get the value at an index of 23. Will this work? 23. Counter object is not subscriptable. So, as expected, we can't just index or subscript items of an iterator. If we want to do that, then we have to add another dunder method called the getItem dunder method. So, and this is how it looks like. Def get item self, then you specify the value that you want to put in your index or subscript. And since both the counter values are integers and indices are also integers, but the indices start at 0 whereas the counter starts at 1, then we could say return val plus 1. So now let me try rerunning this. Let me run this. Now it works. But the problem with this is there's no regulation for how it can be subscripted. Right now it can take on even funky values. For example, I could do, let's say, like 1,000, and this will also work. So right now it's not very regulated. So the way that we can fix that is, first it has to be an integer. So we can say if not is instance val int, then raise type error. Next we can say if val is less than 0, because remember our indices start at 0, raise index error. Okay, and last but not least, if val is greater than or equal to self.val, then also raise an index error. Okay, so now let me rerun this. Now if I try running 1,000, which is out of the bound of the counter, this will throw an index error. And so will a negative number. So negative 109, this will also throw index error. And the reason why I chose index error is so this can emulate other objects that also throw index error for similar scenarios. For example, a list. If I have integers 1, 2, 3, 4, 5, and I try to get an index out of the range, I will also get index error. So that's why I chose index error, to sort of emulate this. And similar to this, let's say we want our manager class to also be subscripted, meaning we could get the employees by their name. Then I could write def get item self name for employee and self.employees if imp.name equals name, then return imp. Okay? And then if you're never able to return an employee, meaning the name never matched any of the employees in these employees, then in that case you raise a key error. Okay? So now let me run this. Now if I try to, let me run this again. Now I can get the employees that Bob manages by name. So I can say this, and now it'll work. But if I specify a name of somebody that's not an employee, then I will get a key error. So Bob Hector, because he is not an employee, I get a key error. And the reason why I chose key error, similar to why I chose index error for the previous example, is because we're subscripting by keys, kind of like a dictionary. Because in a dictionary, take for example the following: if I specified an incorrect key, I will get a key error. So just as a dictionary throws a key error for incorrect key, similar syntax is why I chose key error. So by now you have a pretty good grasp of what an iterator is, how it works, and how to make one. But why should you? Aren't the built-in lists, tuples, sets, range, and so on, aren't they sufficient? The answer to this is, in most cases, memory. The thing is, the built-ins act like more than just sequences. They're basically complete containers. All their items are predefined and stored. But an iterator, on the other hand, isn't. It doesn't store any items, but just the mechanism to create items out on the fly. Think of the former like a tank and the latter like a pump. If our tank is too big, it takes up more space, whereas the pump will take up the same space. Now our pump could be bigger, meaning our iterator might need to do a lot just to spit next. Its logic could be bloated. But the point is, the pump size only depends on the complexity of the next method, where the tank size is dependent on how many items there are. So no matter how complex we make our logic, the tank will always be bigger at some point, the more and more items we put. To see this, just look at the memory difference between the two. Memory of a list grows as its size grows, whereas the size of the counter stays the same. Here I'm going through different sizes starting from 10, 100, 1000, all the way to a million. And for each size, I'm creating a list, but I'm also creating a counter. And then I'm using the sys.getSizeOf function to get the size in memory each of these objects takes up. And if we were to run this, as the size increases, the size of the list gets exponentially bigger and bigger, but the size of the iterator is the same because the size of the iterator only depends on the logic under the next, which stays the same.